So now we have this algorithm, we have seen how it behaves in practice, at least on this particular data set it seems to do something that's reasonable. Now what can we say about theoretical results? Now let's again try to first build up a bit of intuition. So consider an arbitrary matrix Z, and let's for simplicity assume that this matrix is even squared. So we have the same number of movies and people that watch it. So it's a P times P matrix. And now assume that we observe n entries of this matrix, and these entries are drawn uniformly at random. So we have P times P matrix, we pick n entries randomly. And the question that we want to look at is now how many entries do we probably need to look at before we can successfully reconstruct this matrix, at least approximately, or what would be a first guess for the number of entries. So now there are a couple of things that obviously should not occur. So one problem is the problem of empty columns. So if there is a row or a column in this matrix for which we don't see any entries, then there's nothing we can predict. So there's a user, but the user didn't tell you anything about what he likes, then there's nothing you can recommend. Or if there's a new movie and nobody has seen it, then at least in this collaborative approach, there's no way you can tell which users are going to like this movie. Okay, so one necessary condition that we would have is if we do this random sampling of entries in a matrix, we would need to make sure that there's at least one entry in each row and at least one entry in each column. Okay, and now this is now a combinatorics question that I want to ask for you. So now essentially what we have is we have n elements. So here it's written on the slide. We sample n elements. Each element belongs to p columns. How large does n need to be such that with reasonably high probability we have at least one element in each column? Maybe you can try to solve it as an exercise. Maybe you also know it because this is a very famous problem. It's called the coupon collector problem. You need to have at least p log p many samples. It's called coupon collector. So if you remember as school kids, you often had these kind of sticker albums where you have, I don't know, it's soccer championship, and you have like these sticker albums where you can buy stickers. Each pack of stickers contains, I don't know, 10 particular stickers, and your album has 100 empty places for the stickers. So how many of these little sticker packages do you need to buy before you have the album complete? This is sort of this kind of problem. Okay, so I mean the first thing I want you to note is we need to sample at least p times p entries of this matrix, otherwise it's pretty much hopeless. At least hopeless that we can say something about each column. So p log p. P is the dimension of our matrix. P log p is the first answer. Now the second thing, we want to approximate, or we think that our matrix might be a low rank matrix, so say the rank is R. So if we have a rank R matrix, which has is a p times p matrix, then we can describe this matrix by R vectors essentially. So a rank R means we have, say, our singular vectors, for example. So we have R vectors, each of them has p entries. So all we have R times p parameters in these vectors. So somehow we need to, and this is now really wild guessing, but still it helps to gain intuition. So we probably we want to estimate something like R times p number of parameters. And typically, I mean, you cannot hope that we can get away with having fewer than these parameters, because then maybe your matrix might even have a lower rank. So in typical choices, these RP entries could not be compressed any further. So you couldn't just replace them by something that is even smaller. So I now wrote it is plausible, and the question is what is plausible, but now we want to have RP parameters of this matrix, and one thing that you might find plausible is at least that we probably also need to observe about at least R times P entries of a matrix, otherwise it's not going to work. Okay, I mean this is sort of a very rough rule of thumb or hand waving as I've written here. But often these kind of rules of thumb, if you have a good feeling, then it helps you to get some intuition about the problem. Okay, so now we have two conditions. P log P entries from the coupon collector problem to make sure we hit each column, and R times P entries if we want to approximate this with a rank R statement. Now here's the next thing, and this is now a very technical thing that is a bit more complicated. And the condition is called coherency. So assume our matrix that we want to complete looks like this. This is the matrix. It's completely full of zeros, and there's just one entry, 1, in the top corner. And now assume we randomly sample some entries of this matrix and we try to recover it exactly. So this is now about exact recovery in the first place. This looks like a very complicated problem. I mean, from a structural point of view, the matrix has rank 1. So it's really low rank, so you might be happy and say this should be an easy problem. But still the problem is not easy because the entries in this matrix essentially don't have the same importance. There's this one entry that you need to find. If you miss it, you're likely to miss most of the important thing of this matrix or the important structure. And so if we sample less than of the order p square entries, then likelihood is high that we fail to find this entry and the result is going to be wrong. And now there's this condition that is called coherency that tries to catch this particular kind of problem. And the problem is that some entries are more important than others. And if you have this condition, then of course if you just uniformly sample at random and you miss the important ones, you have a problem. And now if you try to formalize this problem from a mathematical point of view, the problem is that the eigenvectors of this matrix are too much aligned with the standard basis of Rp, which means here, I mean, they're perfectly aligned because it's just 1 times the standard basis, the first eigenvector, the first unit vector, and so it's perfectly aligned. So we just need to have like a 1 here, and then this describes the whole vector. But what would be much better if say the coordinate system would be much more rotated, and I would need to have a bit of an aspect of each of the standard basis vectors. And this is now what we try to cover in the condition that is called coherency. So what we now want to do is, we want to measure up to which extent the eigenvectors of the matrix that we're currently looking at are aligned with the standard basis. And now this leads to coherence, and here's the definition. So assume U is a subspace of your original of Rd, and it has dimension R, and say Pu is the projection on this particular subspace. Now we say the coherence of the subspace U with respect to the standard basis, Ei, is defined as follows. So the coherency is going to be denoted by mu. And here's some kind of normalization factor, but the important point is we look at the projection. So we project each of the standard basis vectors on this particular space. And then we evaluate what is the norm of this particular projection. Right? And this here in the front, this is just a scaling constant. But essentially, so what we want to do is we want to project the standard basis on this space, and then if it's okay, and then we call this, we do that for all the d basis vectors, and then we take the maximum, and this is what we call coherency. And maybe to get a feeling for this, let's look at a couple of examples first. So here's the matrix we started with. This matrix has a 1 here and 0 everywhere else. The first eigenvalue is 1, everybody else is 0. Now so the first eigenvector of this matrix is the unit vector. So if I project the standard unit vector on this first eigenvector, I get exactly the same. I get a 1 out of there because these eigenvectors coincide. So V1, the first eigenvector or singular vector of this matrix, in this case it's an eigenvector, is exactly the same as the first vector in the standard basis. So we get the maximum thing that we could get out, namely 1 here. For all the other eigenvectors, this doesn't really matter anymore because this is going to be the maximum value. Recall we have a projection operator here, so this norm can only be, it can't get larger than 1. 1 is the maximum norm that you can attain for a projection, of a unit vector at least. Let's look at the same matrix just with flipped signs, because the problem if you have 1s everywhere and just a 0 at a different place, it's sort of the same problem, we just flipped sort of the entries. And again, if you miss the 0 here, then we are not going to predict correctly at this particular entry. So again, now you can look at the eigenvectors and eigenvalues here, and you can try to compute them. In this particular case, with a number of vectors, with 1, 2, 3, 4, I have a matrix of 5 entries here. This is how the first eigenvector looks like. This is how the second eigenvector looks like. And now this unit eigenvector, this unit basis vector, is an element of the span of the first 2 eigenvectors. And now you can see that if you project the standard vector E1 on this space spanned by the first two eigenvectors eigenvalues, for example, then again you get a 1 here. So again, this is a high value, meaning that the problem is difficult. Now let's look at this other matrix that consists completely of ones. What do we get here? The first eigenvector is the constant 1 vector. Everybody else is 0. If you do the projection, you can just compute it. Like if you project the standard unit vector on this thing, what you get is just 1 over square root of n. So this has a low coherence value. And in fact, this is the smallest value that you could attain possibly. I mean, these are just examples, but they show, I mean, the coherency is sort of a number that changes between 1 over square root of n and 1. And the ones stand for difficult cases. So if the coherency is high, it's difficult. If the coherency is low, we might expect it to be simpler. Okay. And here again, this is sort of, I've written it on the slide as well. So the coherency, the smaller the coherency, the easier. The maximum value is sort of the value of 1. The minimum value is if you achieve this value, and then it's 1 over square root of n. Okay. And sort of here, the general intuition is that coherency is low if all entries have about the same order of magnitude, because then sampling some of them doesn't really, they all have sort of the same kind of importance. Oh, here's one more example, a random rank K matrix. Here I made a simulation just again to get some feeling. So for what would be the coherency of a random matrix? Now start with a rank K. So how do you generate a random rank K matrix in the first place? A P times P matrix that has rank K. So that's not completely obvious, but if you think about it for a couple of minutes, there are many solutions, but this is one. You generate a random matrix of size n times r. And then you simply take the product, m times m transposed. Then you have an n times n matrix, but it has still rank r. So the first r eigenvalues are being larger than 0, everybody else is 0. And now I can sort of, in my simulation, I can vary if r is low. I can now check what happens for the different ranks with the coherency. And here we see the plot that I obtained. So here you have coherence, just without the normalizing factor, so the thing between 1 over square root of n and 1. And here's the rank of the matrix, and what you see is if your matrix is low rank, then this random matrix, the way I generated these matrices is more or less random. So here you might want to hope that there's not one particular entry that is more important than other entries, because all entries have been generated independently by the same kind of process. So somehow the entries should have the same kind of importance, and this is also what you can see here up to a certain extent. So if the rank is low at least, then the coherency is low as well, and the coherency increases if the rank of the matrix increases as well. This was a 100 times 100 matrix, so in the end, of course, coherency is 1. And now the cool thing is you can now prove guarantees for exact recovery of matrix completion in terms of this kind of coherency, and also for approximate recovery. And the guarantees are always of the following flavor, and we're going to see some on the next slides. So P is now the size of the matrix and R is the rank. So the statements typically have a flavor like, with high probability, exact recovery of a matrix is possible if the observed entries satisfy at least a guarantee like this. So the number of entries that you observe, capital N, has to satisfy a certain guarantee. So it needs to be larger than a constant times R times P times log P. This constant depends on the coherency. So if the coherency is low, then this constant is also low. And then this parameter n here, the number of entries that you need to sample, you can sort of forget about the constant, and the number is something like r times p times log p. And this is sort of cool because it says, like, if the coherency is low, this sort of should be the regime where we can achieve something. And now think about the rules of thumb we had. We had one rule of thumb that says we need to sample at least r times p many entries. This was from the rank constraint. And we had this other rule of thumb that says we probably need to sample at least p times log p entries to make sure we have an entry in each column and in each row. And now the bound says if you're in this nice regime where coherency is low, then forget about this constant and we get exactly sort of the best thing that we could get from these two kind of things, namely r times p times log p. That's really so elegant, isn't it? And now the other thing is if the coherency is high, then what you can prove is, I mean, you can't see this from the slide here, but then c times r is sort of on the same scale as p. So you have c times r here is being replaced by a p, so you need to sample about, in the worst case, p square log p entries, which is even more entries than you have. So if you randomly sample from the matrix, by this sampling scheme, you make sure that you have essentially seen all entry at least once. And this makes complete sense, at least in hindsight. Now you have this coherency, which is a parameter that tells you how difficult your problem is. If it's easy, you're in this nice regime where you also, I mean, just consider this is sort of seems reasonable if you have, if your rank is reasonably low, then you sort of maybe forget about the log, but essentially you need to sample linearly many entries in the number of rows of your matrix and also linearly in the rank. If the coherency is high, then there's nothing you can do. Essentially, you need to sample each individual entry of your matrix before you will be able to solve the problem. So then matrix completion essentially doesn't work because you need to see everything that you otherwise might be able to predict. Now the proofs are not so obvious. This is there are steep theoretical results behind there, but if you want, you can try to look at the papers. And here I now have this question, is it a good or a bad result? But I also started to discussing it, and I guess you already found that I find this is a good result, and really I like it a lot. I also want to show you a bit how these theorems look like if you look at them in the original papers. I mean, just also to give you a bit of a feeling. So here's the theorem that comes from Candace 2009. It is really about the exact recovery, and it sort of has this coherency notion. So let us maybe try to decrypt this theorem. So we say M is an n times n matrix, n1 times n2 matrix of a certain rank R. And in your head, maybe think, to make it simpler, n1 and n2 is the same, it's just the number n. We have its singular value decomposition, sorry. And now we assume blah blah, n1 is smaller than n2, that's not important. Now when we do an SVD, the sigma matrix is r times r because it's a rank r matrix, and u is n. So here he just fixes essentially this is the dimensions of the matrices. And now he makes two assumptions. Assume that first, A0, the row and column spaces have coherencies bounded above by some constant mu0. So this is the coherency condition. You say, we said low is good, and they say the coherency must be at most mu0. And this is a constant that is going to characterize our problem. The smaller the constant is, the better the bounds hopefully should be. The second assumption, A1, the matrix has a maximum entry bounded by some particular term in absolute value. This again is another way to measure that there's not one entry that is much, much larger than all the others. It also gives you a bit of the scale of the results. Observe also, so here you have another constant which is essentially mu1. So now we have two constants that tell us to quantify how difficult the problem is. Mu0, the coherency, the bound on coherency, and mu1, so the rest is just scaling, but mu1 is sort of the interesting constant here, which talks about the maximum entry of the matrix. And now, suppose m entries of the matrix, so m is now the number of entries that are being sampled. Like lowercase m are being sampled with locations uniformly at random. And now there's a statement, if m is larger than a certain thing, then, and we are going to decrypt it in a minute, but let's first read it. So if m is smaller, is larger than a certain number, so we sample at least so and so many entries, then if we look at this problem that we want to solve, namely the exact matrix completion, and we solve it, then the solution is unique and equal to m. So we have the exact recovery of the original matrix with probability at least blah, with a high probability. So under all these assumptions, if we sample enough entries, then with high probability we have exactly recovered our matrix. Okay? So from the outline, this sounds like the statement we might want to have. And now you need, but to decrypt it, this takes a bit of time. So now we need to look at these entries. So here it says we need to sample so and so many entries. And so here we see essentially this, so here we have the rank times the dimension of the matrix. So this is essentially what was P in our previous slide. And here we have something like log P again. And there are a couple of constants in here. And in particular, these two constants, mu1 and mu2, that characterize how difficult the problem is, they enter the bound in terms of a constant. Okay? And then we have also the other thing, the probability. This whole statement holds with hopefully high probability, and now you can check with which rate the probability decreases. This is something that is a bit more complicated, but you can now try to see whether the probability that it typically should decrease as your problem gets simpler. Okay. And and what I forget to mention here is that the star is the trace norm of the problem of the matrix. Okay, so this is really we want to find the matrix the smallest trace norm. Okay, here I have another statement of this of a similar theorem that's now taken from a different paper. So this is now for approximate matrix recovery. So previously we had that we want to exactly recover the matrix, and now we want to approximately recover the matrix. And here's yet another theorem. So now observe, so we have now, and of course the notation is always a bit different and different from my slides because it's taken from different papers. So assume we have a low rank matrix M that has some noise on it, on top of it, which is C. And the whole matrix is called N. And now we have a matrix. Again, we can measure the incoherency of this matrix. It has rank R. We observe a certain number of entries, E, and these entries are sampled uniformly at random. Again, now we make an assumption on the minimum and maximum singular values of this matrix, and in particular, we look at the ratio of these minimum and maximum values and call it kappa. And now we say M hat is the output of the optimal algorithm. I think this is the soft impute algorithm. I'm not really sure. So assume that M hat is now the estimated matrix. Then there exists constants such that if the number of entries that we sample is larger than something, so same kind of structure, then with probability at least something that is really high, the error of recovery in terms of the Frobenius norm, M hat minus M, Frobenius norm, is bounded by a certain term that decreases if the number of sampled entries gets larger. It sort of scales with the amount of noise that we have. It scales with N and kappa. So there are certain parameters that sort of quantify how difficult the problem is. But so you can now give results on the approximate recovery. And the number of entries that we need to have is sort of on the same order of magnitude as before. If you try to decrypt this complicated statement here, essentially we have like N times R times log N times mu. So the statement is very, very simple to this, similar to the statement we had previously. It has the same flavor of result, but now for approximate matrix recovery. Good morning. While recording the lectures last time, I got interrupted by my daughter, and now it's a new day, and I'm going to resume from where we stopped. So in the last lecture, we came until the point where I explained the theorem about the approximate recovery. And now we want to look at simulations to see whether the theorems that that have been proved to hold in theory also manifest themselves in practice. This is always important, even if you work on theory, because you can often prove theoretical guarantees, and they are of course correct. But often these guarantees are also statements that make strong assumptions, or that make statements about very large sample size or so. And it is important to see whether these statements sort of can be recovered in simulations as well. And typically this is the case, but it's a very important step even if you're working on theory. So let's now check whether if we try to make simulations about matrix completion, the algorithms behave the way we think they should behave. So the first thing we need to consider is how can we generate a random low rank matrix? Because we now want to generate some toy data, so we want to have a ground truth matrix that has low rank, yet is symmetric, and we want to, it doesn't even need to be symmetric, sorry, but it needs to be some random low rank matrix. And as I've said already before, you can't simply sample entries randomly independently from each other, because this is not going to result into a matrix that has low rank. So what we're looking for is a model by which we can generate a matrix that is as random as possible, but has a fixed prescribed rank and of course also a fixed size. You might want to lean back and think for a minute on how you could generate such a random matrix. Okay, maybe you have seen how it works. So here's one approach that you can try. So what we do is, in the end, we want to have a matrix that has size p times p, and the rank of the matrix is supposed to be R. Here, R. Now what we're going to do is, we generate two matrices, U and V, and these matrices are rectangular. They're not square matrices, so they have the dimension R times p, p times R. And for these matrices, we sample random independent entries. You could sample them just binary, 0 or 1 values, but what we're doing here in this simulation is we sample each entry independently from all the other entries by a simple normal distribution. And you will see later we are going to look at some figures. So the values one chooses here, or the authors choose here from which I took the figures, is p is 20, so that's the size of the matrix, of 40. The rank is something like 1 or 5. Simply to get you a feeling. So typically you start with reasonably small problems, even though in practice then you want to apply it to much larger things. But to understand what's going on, you want to run the simulation on your laptop, you want to press a button and you want to see the result immediately, so maybe start with a small scale problem. Okay, so we generate these matrices U and V, and then we define a new matrix that is called Z, which is a product of U times V transpose. Now observe, the dimension of this new matrix is p times p, and this matrix also has rank R. If you don't know why this is true, that the matrix has rank R, I encourage you to think about it and come to a solution, because that's important. Now, what we have done so far is we defined our ground truth model from which we want to simulate the data. And now we need to generate toy data from this model. So what we now do is, we have this ground truth matrix, which is sort of, say, the matrix of the observed ratings of customers, for example. And now we sample n entries from this matrix independently at random positions. Because this is also the assumption that we always make in the theorem, that entries have been sampled randomly, uniformly from the matrix. Now we have our data, so we have the incomplete matrix, and now we want to complete it and want to look at how do the algorithms perform. So what do? We now apply our algorithm, for example, soft impute, to complete. So taking the incomplete matrices, we complete them and estimate a new matrix Z hat. And then we want to compare the matrix Z hat to the true original ground truth matrix Z. In some norm, you can now look at different kinds of norms. And hopefully you would like to achieve that the matrix Z hat is close to Z. And then what we are going to do is, because this is, of course, there's lots of randomness in this process here, and the sample size is not yet so large, typically. So what we do now is we are going to repeat this experiment very often. And then, like for each particular fixed parameter setting, we repeat the experiment very often and then report the fraction of how many of these experiments were successful, in the sense that we correctly recovered the matrix. So in this first experiment, we are after exact recovery, and we are also in a noise-free setting. So we really want to check, can we exactly recover the ground truth matrix. And here is a simulation, or the results of the simulation, which I took from the book Statistical Learning with Sparsity. Let's now first of all try to digest the plot. So what we have here on the left-hand side, so we have two panels. On the left-hand side we have the situation where the original rank of the matrix is 1. And at the right-hand side we have the assumption that the matrix has rank 5. On the x-axis you always see the proportion of missing entries. So if, say, 0.2 of the entries, 0.2 means that 20% of the entries are missing. So here we still have observed many of the entries of the matrix. At 0.6 we have already seen less than, like, only 40%, so 60% of the entries are missing. So the problem should get more difficult when we go from left to right, because we observe less and less entries. On the y-axis we have the probability of exact completion, which means in the best case it would be 1. So we repeat our experiment say 100 times, and the probability of exact completion says how often were we successful. If the probability is 1, it means we have been successful all the time. If the probability gets lower, we are less and less successful because we can only exactly complete the matrix in, say here, for example, if it's 0.2 in 20% of the cases. So, and at the y-axis, high is good. Okay, so now we know what is on the axis, and then we have two plots. One for so P is the original size, the dimension of the matrix. It's either a 20 by 20 matrix, or that's the orange curve, or a 40 by 40 matrix, that's the blue curve. And now, typically what you should do if you run a simulation like this is you need to convince first of all, probably you should build an expectation on how the curves should look like. And then you compare your expectation with what you see, and often these things don't match, or there are things you can't explain, and then you need to consider what's going on. So let's look at this figure. So the first thing is that the curves, like I'm now in the left panel, the curves decrease if we go from left to right. And that makes perfect sense, because the less entries we observe, the less likely it is that we correctly recover the matrix. So this is what we would expect. We can maybe also compare the figure on the left to the figure of the right. So in the left we have the true matrix has rank 1, at the right the true matrix has rank 5. And now when we compare these figures, we can see that the problem gets more difficult if the true rank is 5, because these curves decrease much, much faster on the right hand side than they do on the left hand side. So this is good, or this is what we would expect, because the higher the rank of the original matrix, the more difficult the problem is. Okay, so far so good. Now there's a third aspect that I find not so obvious. Namely, we have two curves here. We have the green and the orange curve. The orange curve is the case that the original matrix is 20 by 20, and the blue curve is that the matrix is 40 by 40. And honestly, if I would have predicted what would happen, I would have said completing a 20 by 20 matrix is easier than completing a 40 by 40 matrix. So I would expect that the curve that corresponds to the 20 by 20 matrix, the orange one, is above the blue one, because I would think if it's easier, then the likelihood of success is higher. So this would have been my expectation. If we now look at the two plots, we see that it's the other way around. And this is now a place that really deserves explanation, and in particular, if this is a situation like you implemented an algorithm yourself and you want to understand what's going on, then this is really something to look into. And I have, so the summary, like on the slide here, I summarize what I've said so far. So the first two easy points, like a problem gets harder when we have less entries, the problem gets more difficult if the matrix has a higher rank, that's all clear. And here is now the observation that is a bit confusing. For a fixed R, the likelihood of exact recovery increases with the dimension P. So the problem gets simpler if the original matrix is larger. Okay, now to really understand what's going on, one would need to dig into here. And admittedly, I didn't spend 2 days in trying to find out what is going on here. I trust that the authors have done the simulations correctly. I mean, the first thing you always check is whether you maybe mixed up the legend in your figure, and maybe you simply put the wrong labels at the two curves. But I would guess that the authors did a good job here and put the correct labels. And now you need to start to look into what might be the reason that you observed this unexpected behavior. And I put two possible explanations on the slides, at the same time admitting that I didn't really try to figure out whether these explanations are true or whether there's yet another reason. Because this is sort of, I also want to show you how to approach such a problem. This would be what you would also need to do if this would be your experiment. So let's start with possible explanation 1. So my first explanation says, to recover a rank R matrix of size P, you intuitively need to recover R times P parameters. Okay? Now the matrix has about P square many entries. And these P square many entries are the source of information that you have. So the ratio between what you want and what you see is like, this is what we are looking for, and this is sort of the, and P square is the number of possible sources of information that we have, which is R over P. So for a fixed R, this gets of course better when P increases. This might be one explanation. So because the matrix has so many more entries, somehow the problem gets easier. Like more entries compared to the number of parameters that we want to recover. The second explanation is if we look at this recovery theorem that we have seen on the previous slide, what we can see is the following. So everything else being fixed, the necessary number of samples that we need increases with P log P. This we have already discussed. But we also need to look at the probability of exact recovery, because this one increases as 1 minus 1 over P cube. And now what you can do is you can compare the probability of recovering the entries from MP measurement, and this probability would be higher if P is larger. And so there's now a trade-off between the error that you're going to make and the probability of recovery. And it might also be that if you rewrite the theorem, that then you can see that this behavior in terms of P is going to happen. So you could, for example, try to rewrite the theorem in such a way that the probability of recovery is always the same. So you fix the probability of recovery, say 95%, and then you check how many samples do you need, and then you look at how does it change in dependency of the original dimension of the matrix. And perhaps if you do that, then you would see that this behavior that we can see in the plot also is implicit in your theorem. But as I said, all these explanations are a bit ad hoc. I didn't really spend all the time to dig out why the two curves behave this way. This would take me probably a day to figure out. Maybe it's just a matter of an hour, but maybe it's also a day or two. And I didn't want to spend the day. But this is sort of the way I would start approaching this problem. And maybe I think as a lesson to you, it's maybe sometimes better to not show you what are the results that I get after sitting and staring at something for 1 week, but to show you how I would approach such a problem, and this would be the approach I would take. And then if none of the two explanations make sense, I would either try to find a third explanation, or maybe I would start to re-implement my simulation and would check maybe after all there's a bug. And in this way play so long until you really understand what's going on here. Okay, this was the noise-free case. Now let's look at a noisy setting. So in the noisy setting what we do is we generate the matrix as we had it before, but now we add a Gaussian noise to each of the entries. So on each of the entries, so say you have your ground truth matrix, but on each of the entries we now put noise with standard deviation 0.5. So we now, instead of the matrix Z, we now observe a matrix that I simply called Z noisy. And now we try to reconstruct the matrix while observing partially the entries of Z noisy. And what we're going to do is we're going to plot. And what are we going to plot? Some kind of error curve, of course. And what the authors of the book, where I took the figure from, did is they plotted the average relative error, which is the average Frobenius norm error. So the difference between the true matrix and the estimated one. Of course, the true matrix without the noise. With the noise, sorry. So you take the matrix Z noisy, and then in the denominator you normalize by the standard deviation of the noise. This is some kind of relative error. And again, if you see such simulations, or in a paper they say, I'm going to plot the relative error in this way, I mean, this is maybe not really a standard form of an error that you would see in millions of textbooks. So maybe the first thing you should consider is, well, what is the best thing that we could expect to come out here? And I'm going to tell you that the best average relative error would be about 1. But maybe you need to try to understand why it's really the case that the best average relative error for this kind of experiment is 1. I think it takes maybe 5 minutes. It's not immediately obvious. And here are now the results. So it's the same kind of setting as we had on the previous simulations. Here we have, on the left side, we have the rank 1 case. On the right side, we have the rank 5 case. On the x-axis, we have proportion missing. So the problem gets more difficult the more we go to the right-hand side. And the average relative error is sort of, so now observe this is now error, it is not rate of success. So here lower is better, and the dashed line is at 1, this is sort of the best you could hope for. And the more you deviate from 1, the worse the result gets. observe that here, I mean, it's important, like in the previous plot, it was good if the curve was high, now it's good if the curve is low. This is in fact not a very good style. Typically within the same chapter of the book or the same, I don't know, paper, you should either stick to error or to rate of success or accuracy, because otherwise it's always confusing. Anyways, I mean, we can cope with. And now let's look at it. So, I mean, the first thing we see is indeed the error increases if the proportion missing increases, which makes sense. This is what we would expect. What we also see is, if you compare the left figure and the right figure, is that the error increases when the rank is higher. So in the rank 1 case, the error, say for 60% missing, it's maybe 1.25 or so. And here in the right hand side, the error would already be something like 2.5. So the problem gets considerably more difficult if the rank of the original matrix is higher. Also observe, maybe to get a feeling for what this average error is, that an average error of 2 is something that's already pretty large, and an average relative error of 3 is probably something that is too large to be of practical relevance. Simply, if you think, for example, you have Amazon ratings, they are between 1 and 5, you put a certain standard deviation. So, okay, you can't look at the absolute numbers because it's relative error, but essentially it means the error here, the error is twice as large as the noise, for example, in your figure. Okay. Now, with this, I want to conclude this chapter on low-rank matrix completion, and the neighbors start to do their lawn, which is also annoying. Let me try to finish that. I want to look at the literature first. Of course, this field is still reasonably young. I mean, looking at the history, so there's this first PhD thesis by Faisal, who took the nuclear norm as a surrogate for the rank, and this was sort of an important step. And then there are a couple of seminal papers. There's the one by Natis Repro in 2005, which gives the first kind of generalization bounds. And then Candes and Recht, who came up with all this mathematical formalization of when is a problem easy to solve and difficult to solve. And the Netflix challenge, just for the historical perspective, was between 2006 and 2009. And the book by Hastie, Tibshirani and Wainwright is 2015, I believe, and we're now 2020, so this is still reasonably new, even though, of course, many of the things are already, I mean, well understood.